Hello everyone, today we'll be solving the problem number 1325, delete leaves with a given value. So what the question states here, we are given the root of the binary tree and an integer target. Just give me a second, 1 second here. Yeah, we are given the root of the binary tree. You can clearly see here, we are given the root of the binary tree and an integer target. Also, we have been given an integer target. So we have to delete all the leaf nodes with the value equal to the target. We have to delete all the leaf nodes that leaf nodes with the value equal to the target. So one criteria or the condition that I have mentioned here is after deleting, if the parent becomes a new leaf node, after deleting, we have to delete all the leaf nodes that is with the value that is equal to the target, right? So here after deleting, if the parent becomes a new leaf, if the parent becomes a new leaf node and its value is also target, then we have to delete it as well. Then we have to delete it as well. So I'll read this one little slow. After deleting, if the parent becomes the new leaf, if the parent itself becomes the new leaf, right? So we will be deleting certain nodes. After deleting certain node, then if the parent itself becomes the new leaf node and its value is also equivalent to the target, if the parent value that has become leaf, right? Then if its value is also equivalent to the target, then we have to delete that one as well. Then we have to delete that one as well. So we have to repeat this process until no such leaf exists. So we have to repeat this process until no such leaf exists. So this is the criteria or the condition that they have given, right? So we have to return the root of the modified tree. What we have to return? We have to return the root of the modified tree. That's what we need to return here, right? So I hope the question is completely clear. Let's come to the example part here. Let's come to the example part. Let's do one thing. Let's discuss the approach directly by considering the first example. For this particular problem, let's discuss the approach directly for this by considering example 1. So here we will be making use of post order DFS traversal. Post order DFS traversal. So I'll just write here post order DFS. So we'll be making use of the post order DFS travel for this particular problem. So if you remember, we have solved many problems by now, right? So including JavaScript and Java, we have solved n number of problems using the pre-order, in-order and the post-order, right? So we will be making use of the post-order DFS traversal. So, and one more thing I want to tell here is post order follows the order left followed by right followed by root or the node. So I'll just give here root. Left means left subtree followed by right means right subtree followed by root means the root node, right? So this post order traversal, I mean post order follows the order left root and left right and root, left right and root. So just keep this in mind. This will help you while writing the code or while discussing the approach both, right? So I'll just delete this one. Let me delete this one. Yeah, first here let's consider the example. We have been given root 1 2 3 2 null 2 4. This one we are considering the diagram. This one 1 2 3 null null 1 2 3, sorry, 2 null. Here we don't have anything, so we will be considering this one as null. 2 and 4, 2 and 4. The target we have been given 2 here. The target we have been given 2 here. So what we need to do accordingly with the question, so we have been given the root of the binary tree and integer tag. We have to delete all the leaf nodes with the value equivalent to the target. The target value is 2 here. We have to delete the nodes with the value 2. And if the root node becomes the leaf node after deleting the this one, what do we call, after deleting the leaf node's value that is equivalent to the target, if the root node becomes the target, this one, what do we call, leaf node, and that value is equivalent to the target, then we have to delete that node as well. Then we have to delete that node as well. That is what they have given in the question. See here, now we have 1 2 3 2 null 2 for this one. 1 2 3 2 null 2 for this one we have, right? So now we have the value 1 here first, this one followed by 2, this one followed by again followed by 2, again followed by 2, right? So this one is 3, this one is 3, and this one we have 2 and 4. This one we have 2 and this one we have 4 here. This one we have 2 and 4 basically, right? So 1 2 2 and 1 3 2 4 we have here. So the target we have been given 2. The target we have been given 2, right? So the first step here would be we will first remove all the leaf nodes with the value 2. We will first remove all the leaf nodes with the value 2. We will remove leaf 2, that is left of 1. This one I'm speaking of. We have 2 here, right? So let me do one thing, change the color here. Sorry. So here, let me consider this example itself, this one itself. I don't have to draw this one. So we will remove this one. We have value 2 here. We will remove this one. We will remove this one. Left leaf 2 means left of 1 basically. Left of 1 and leaf 2 left of 3. Leaf 2 left of 3. This one I'm speaking of. This one I'm speaking of. Leaf 2 left of 3. Right. So now 3's left child is gone. 3's this one 3's left child is gone. 3's left child is gone. 3 is not leaf. 3 is not a leaf now. 3 is not leaf. So we will continue. We will continue. Right. So now we will check again. Now root is 1. Root is still 1. Right. Root is still 1 and left we left null. We have the left null because we have deleted the value 2 here. We have deleted the value 2 here. So this one also we have deleted. This one also we have deleted. So the left value is null. So the left value is null. Right value we have here 3. Right value for the root we have here is 3. Right value we have here is 3 with the leaf 4. 3 is still having the leaf 4. So 2 was having the leaf 2, that also we deleted. I forgot to delete that one primarily first itself, right? So here in this case we don't have any value at the this one left side for the root. Now we are left with 1. This side we have null. We don't have anything. We don't have to represent this one at all. Only we have right side. Basically this has become the right skewed tree now. 1 3 4 1 3 4 we have, right? So 1 3 4 we have, right? 2 we have deleted. From this one we had 2, that one we have deleted, so we don't have to consider this one. So we have right skewed tree now. This is nothing but 1 3 4 1 3 4. This is the tree we have now. This is the tree we have now, right? So now we will check again. Root is 1, left is null, left is null, right is 3. Right is 3, root is 1, left we have null, big null, so we don't have anything here, right? Right, this one null. Right we have 3 and with the leaf 4. Right we have 3 with the leaf 4. This one I'm speaking of with the leaf 4. So we don't have, we have not left with, we are not left with anything basically here. Nothing else to delete here. Nothing else to delete here. Nothing else to delete here. So now we have the final tree 1 3 4. This one we need to consider 1 3 4, right skewed tree basically. It is completely skewed at the right part, right? So this is right skewed tree. We can consider right skewed tree. So result would be 1. At this part we have to, we have null, so we will this level we have value 3, so we'll be considering null 1 null 3 and again. So we have here for 3 we have at this point of level we have the value 4. For left subtree we'll be considering null, so the value would be 1 null 3 null 4. 1 null 3 null 4. So this is the output that we basically got after performing the post order DFS traversal. The solution that we got here is 1 null 3 null 4, which is equivalent to the output that they have given for the question, that they have given for the example 1 here. See, 1 null 3 null 4, 1 null 3 null 4. This is how we will be performing the post order DFS traversal, right? So now whatever the answer that we got is equivalent to the output that they have mentioned for the example 1 within the question. So our approach works absolutely correct in this case. Our approach works absolutely correct in the case. One more thing, again I'm telling, we know that post order traversal follows the order left, right and root. Left, right and root. Just keep this in mind, man. So I'll just delete this one entirely. Let me delete this one entirely. Just give me a second here. Yeah, let me delete this one entirely. So same thing you can check for example 2 and 3. Same thing you can check for example 1 and 2 and 3 basically, right? So we have already discussed the example 1. So I insist you to try out the same thing for the example 2 and 3. Same steps. You can perform same steps. You can just perform PF this one. What do we call? Post order DFS traversal, and you can go with the same steps that I showed for the example 1. For example 2 and 3 or 3. Example 2 or example 3. So now, as we are completely familiar with the approach, let's discuss the complexities part very quickly. So what will be the time complexity here? The time complexity would be big of n. So why it is big of n here? Because we are visiting each node exactly once. We are visiting each node exactly once. So the time complexity is quite obviously big of n here. So what would be the space complexity here? Space complexity would be big of h here. Space complexity would be big of h because we will be making use of the recursion stack. So we are going with the post order recursive DFS traversal. Recursive DFS means DFS traversal basically. We can call that one as recursive DFS, right? So here, due to the recursion stack, the overall time complexity would be big of h. So nothing, h is nothing but the height of the tree here. So overall space complexity would be big of h. So we can consider n. The recursion depth can go up to big of n, but see, for the balanced tree, it would be big of logarithmic something, and for the skewed tree. So in this case, the output we got right skewed tree, right? So right skewed tree. In the for the this thing skew tree, it would go up to big of n, right? For the balanced tree, it would go up to big of logarithmic something. So it's better to go with the height of the tree rather than big of n or big of logarithmic something, right? So that is the reason I have given here big of h. So the time complexity and the space complexity for the code that we'll be writing in the future would be big of n and big of h respectively. Now, as we are completely familiar with the complexities part and the approach part, we are good to write the code. Let's start writing the code, right? So here, the first step, the first step here would be this one, the base case, right? So if the tree is empty, then we have to return null. If the tree itself is empty, we don't have any value, then we have to return null in that case, right? So here, I'll just go with if root equals null, then we have to return null. Or we can just write if not of root, then we can directly return null. That also we can write. So I'll just write if root equals null. We are comparing with the value null, right? So means if the value doesn't exist at all. So if the tree is empty, then we will return null. This is fine. The next step is we have, as we had discussed in the approach, we will be going with the recursion. So we will be recurring for the left and the right subtrees. We will be recurring for the left and right subtrees. So this one I'll just go with root dot left. This one will be remove leaf nodes. Remove leaf nodes. This one, yeah, let me give here remove leaf nodes. Root dot left comma target. So this is fine. And also I'll just go with root dot right. So this one, let me assign this one to the let me go with the same thing. Instead of the left, I'll make this one right. So we have successfully recurred for the left and right subtrace. Now what shall we do? After the recursion part, let's do one thing. Let's check if the current node is a leaf, right? Let's check if the current node is a leaf and its value is target and its value is target. So let's write the code for that. So I'll just go with if root dot left, this is equal to null, and root here, yeah, root dot right, this one, this is equal to null, and also root dot value equals target. So here in the question they have mentioned that if the child of the root, if the child of the root is equivalent to target, then also we have to delete, then we have to delete that one. And after deleting the child of the root, if the root becomes the leaf node and its value is equivalent to the target value, then also we have to remove the root node which has become the leaf node now, right? So for that one we have considered here root dot value equals target, right? So for that one we have considered root dot value equals target. Don't get confused here, right? So within the if condition, we have to delete the current leaf node. Means I will go with return null. I'll go with return null. So the final step we are left with is we have to return the current node, nothing but root here. I'll just go with return root. I'll just go with return root. Let me format the code once and let me hit the run button. Let me format the code once and let me hit the run button. So here, um, the sample test cases are getting passed. The sample test cases are getting passed here. So as the sample test cases are getting passed, let me hit the submit button quickly. So I hope all the test cases gets passed, man. So let's see. So yeah, you can clearly see here all the test cases are getting passed. Means the code works absolutely correct for all the test cases. So here, I hope. What can I say? Yeah, I hope the solution part is completely clear along with the approach and the complexities part. For now, this is it. Thanks for watching, guys.